Okay. Hello, everyone. Good late morning. If it's late morning for you, good afternoon if you are up since 6. So I want to welcome you for our inaugural BIDMaP seminar of the semester and academic year. I'm Christian Borgs. I'm the director of BIDMaP. BIDMaP stands for Bakar Institute for Digital Materials for the Planet, of Digital Materials for the Planet. And we bring together AI with material science and chemistry to create materials for the good of the planet. And this is the first of our weekly seminar. We always have it Thursdays from 10 past noon until 1. There is usually lunch, so if you are sort of drawn by that, you can come back to enjoy the lunches at our seminar. And the seminar is run together with two colleagues from physics, Urosh and Joshua, from physics and astronomy. And we switch roughly weekly on themes where it's AI for materials and chemistry or AI for physics and astronomy. And today we'll kick off this series with a panel on unlocking unprecedented domains in computational chemistry with massive open AI models and datasets. So let me welcome our panelists, Ray from Meta, Aditi, one of ours, and Sam from up the hill from LBNL. So please welcome the three. Okay, and before I introduce Sam, just a few remarks on how we're going to schedule today. So normally our seminar is Berkeley time, so it starts 10 past punctually, which we won't do today with the introductions, and stops punctually at 1, which we also won't do today. So if you have to run out at 1, don't be shy, just run out, but we'll give our panel more time to interact with you afterwards. We have coffee and a little sweets afterwards, and we will leave it open whether you discuss until 1/2 with them here or whether you let them get some coffee at 1/4 and move over. So that will be fluent today. With that, let me just say a few words on Sam. Sam is a research scientist at LBNL. He's a leader at the intersection of computational chemistry, material science, high-performance computing, and machine learning. He has a PhD in chemical physics from Harvard. So like me, he is a physicist originally. Well, he's a chemical physicist. I'm not a chemical physicist. And he's pioneered the use of self-correcting molecular simulation workflows to construct chemical reaction networks. And of relevance for today, he has a research team which develops novel data sets and representations for ML for chemistry and materials. And more specifically, he's one of the co-creators of the OMol25 dataset, which is one of the two topics, or maybe the main topic. I'll let you discuss that and determine it for today. With that, I let Sam introduce the rest of the panel.
Thank you so much. All right, well, don't want to give short shrift. Ray Gao is a research engineer at Meta, and it was a huge part of both OMol and the universal model of atoms that we're going to hear more about. And then probably, I assume, Aditi Krishnapriyan requires no introduction in this audience, but a rising star in machine learning and AI for chemistry and materials here at UC Berkeley. And we're really excited to be here today and tell you about some of this work and to see the great turnout. And specifically, I just want to start by making sure we're all familiar with what the point of being a computational chemist is, or what a computational chemist does when we do atomistic simulation. Given some 3D atomic positions, we can predict the total energy and the force on each atom. This allows us to do, for instance, Newtonian dynamics by iteratively updating our atomic positions, or run geometry optimizations, calculate free energies, elucidate complex reaction pathways, and time dynamics. Generally get atomistic insight for complex systems that allow us to develop new materials, develop new drugs, etc. So then the question becomes, how do we calculate those energies and forces in order to run these simulations? We can use a classical force field, which is quite fast, but can't describe chemical reactivity very well, or typically at all. We can use density functional theory, which is kind of the best trade-off for, or has been the best trade-off for decades of kind of accuracy and speed, which is to say it's still quite slow. Now we're, in this day and age, we're kind of in the midst of a revolution where we have these machine learned interatomic potentials that are trained on DFT data with the promise of delivering near DFT accuracy with near classical force field speed. And, if we could do that, then you can get kind of to length scales and time scales and to the level of insight that was never be possible with direct quantum chemistry simulations or with classical force fields. But the accuracy of these methods depends critically on the training data that you have available. So this whole field has just been moving so quickly in the last few years, but a lot of the work in the space has been focused on materials. And partly that's because of the great work of the materials project here at UC Berkeley and LBL. In 2022, they put out this MP-TRAG data set. And then in 2023, this Mat Bench Discovery Leaderboard that I'm guessing quite a few of you in the audience are familiar with. And I just want to call out kind of this MACE MP0 model, which was really kind of revolutionary for its time, because an MLIP trained just on crystal unit cell relaxations was shown to at least give kind of qualitatively reasonable things for a huge range of domain applications, all the way to like hydrogen combustion, which is about as far from crystalline unit cells as you could imagine. It wasn't perfect, but it was stable. It was reasonable. And that really opened my eyes to kind of the power of these machine learning potentials and their ability to really revolutionize this space. Now, of course, since, the 2023, when MACE MP0 was originally trained by someone in the audience, actually, we've seen, big improvements in kind of model performance. But you can only get so far with architectural improvements. Often it all comes back to the data. And, last year in 2024, the ferrochemistry team at Meta released the open materials dataset, which is kind of 60 times larger than MP-TRAG, higher forces, further out of equilibrium, more diverse sampling. And now if you look at kind of the Mat Bench Discovery Leaderboard, all of the top models are trained on OMol25. So just to show that kind of with more data, with better data, you're going to get better models. And I think the consensus in the community at this point is that atomistic simulations for well-behaved crystal materials should always start with a pre-trained machine learning potential before you kind of go to expensive density functional theory. So that's like really a paradigm shift in how people do atomistic simulations. Just looking a bit more generally, this team at Meta has been a major force in the space. First starting with kind of these huge data sets on adsorbates on surfaces for catalysis, then moving to direct air capture of CO2 in metal organic frameworks, and then to materials. And the reality is that the computational resources that they have at their disposal, just with kind of excess compute not being used for the social network at Meta, allows them to generate massive data sets that really change the game as far as these MLIP models. And unlike most of the other companies in this space, these data sets are released fully open source, which is a pretty incredible resource for the community. But if you look at this kind of roadmap, there's a clear gap, and that is molecular chemistry. And that's what I'm really excited to tell you about today, is the release of the Open Molecules 2025 dataset, which happened a few months ago and has been generating quite a lot of excitement in the community. So OMol was a huge effort between multiple national labs, multiple companies, multiple universities. And, we were really able to bring this amazing team together because of, ferrochemistry's commitment to open source. That's why all these researchers were kind of willing and excited to work together and build this. We used a huge number of sampling strategies trying to capture much of kind of the chemical complexity of chemistry. And, the domains covered by the data set include small molecules, electrolytes, biomolecules, and metal complexes. The complexity and the accuracy of this data set goes way beyond any other data set of its type that had ever been created. And compared to the 400 million core hours used for the previous data sets from ferrochemistry, OMol used over 6 billion core hours, which Perlmutter, our favorite supercomputer here in Berkeley, the CPU partition of Perlmutter puts out about 2.5 billion CPU core hours per year. So you're talking on the order of like 3 supercomputer years worth of compute it's pretty staggering. And that allowed us to use an incredible level of theory and get real accuracy and complexity that we think is going to deliver a lot of value for a lot of applications in chemistry and materials. This is classic to throw up a heat map on the periodic table. Previous data sets of molecular DFT for training MLIPs were traditionally limited to 14 elements for AIMnet2, 17 elements for SPICE2. QCML was released by a team at Google DeepMind a few months before OMol. That had 79 elements, but has some pretty major limitations, which I'll mention. OMol covers 83 elements. Each number on this table is the number of snapshots in the data set containing that element. And if you're used to seeing these for materials, this may not look that impressive, but in the molecular space, all this D block and even F block coverage is pretty insane. And I think there's a lot of chemistry I know people in the audience and myself care a lot about that uses these transition metals. And this kind of really unlocks the ability for these models to actually get to that really complex and impactful chemistry. But it's not just elemental coverage that matters. I care about things that are charged and open shell. And previous data sets were limited to kind of closed shell species of various charge. AIMnet2 went a little bit farther in the charge. QCML had a little bit of open shell species. OMol goes up to 10 unpaired electrons from -10 to +10 total charge. Just a stupendous expansion of the complexity compared to any previous data set. And it's not just the charge, it's also about the size of the systems. Previous data sets would go up to 80 or 110 atoms. And here, this is where kind of QCML has this major limitation. They only go up to 26 atoms in a snapshot, just one isolated molecule. So, good on them for 79 elements. But if you only ever have one isolated molecule, you're going to have some major limitations. This was a quote in the OMol Slack right after QCML came out from co-first author Daniel Levine. The richness and challenge of chemistry is mostly in the intermolecular interactions, or I would say especially in the interplay between intra versus intermolecular interactions. If you only ever have a single isolated molecule in your snapshot, you're not going to be able to capture that. But because we go up to 350 atoms in our snapshot, we can capture that richness of chemistry, including ligands bound in protein pockets, metal complexes with large ligands, chunks of electrolyte and ionic ligands, and actually where kind of these long-range interactions are really going to be massively impactful. And those are also what often dictate macroscopic properties. Just looking at the raw number of atoms simulated in the data set, it's basically an order of magnitude larger than any previous data set, 2 orders of magnitude larger than kind of the canonical data sets in this space. But it wasn't just bigger, right? It's also a better functional, a better basis set, a tighter numerical grid. And that is, the ability to go bigger, better, and more complex all at the same time is just really exciting. I'm not going to go into how we generated the data set. You can find a talk of mine on YouTube where I do. You can read the paper. But just to say that this is basically the way the data set is made up. And every single one of these slices is basically a different, group of people who wrote the code and generated the snapshot. Each pie chunk, each slice of any one of these pies would have been a world-leading data set in itself. And we did all of it together at once as part of OMol. And this is the last thing I'm going to say before handing it off to Ray is that, evaluation of model capacity, accuracy and capacity capabilities is a crucial part of machine learning potentials and understanding where we can use them effectively. And, OMol also include the development of a whole bunch of really comprehensive model evaluations. And our leaderboard is going to be going live very, very soon, just to give you, kind of a taste of what's to come. It's not just kind of the structure to energies and forces that we're used to seeing, but also specific tasks like how well can we calculate the interaction energy of a ligand bound in a protein pocket? How well can we capture the minimum energy conformer? How well can we do ionization energies and electron affinities? And some of these evaluations we already do with baseline models already do very well on, and some there's a lot of room for improvement. So we kind of expect to see people compete on this leaderboard and drive down these errors as models get better and better over the coming months and years. And with that, I'll pass it off to Ray.
Hey, everyone. Okay, so now we have this giant data set. Let's go back to talking about the models for a bit. So for those people who are familiar with MLIPs, where like ML atomic potentials in the room, we know that in the last couple of years, there's been like this huge explosion of these models. right? And the pattern has been that they've been kind of specific on certain domains, right? There's a ton of models for materials. There's some models for molecules, and then catalysis and MOFs and so forth and so on. But the kind of key is they've been kind of very single domain. So let's look at the materials again. So Sam brought this very influential math bench discovery leaderboard and from the materials project. And the trend here was that there's a lot of these models, but they're all kind of very small, right? They're kind of in the millions or tens of millions parameters. And this is because to get to the top of this leaderboard, you don't need that big of a model, right? We're already getting very close to like 90% F1. And then this has been doing so well on this benchmark that people have been pushing down the accuracy in trade-off for speed. So let's figure on the right, you see that like the latest papers, people are like, oh, I don't care about 94% F1. I can just go 90% and I get a 10 times or 100 times faster model that I can run my simulations with, right? So that's perfectly fine. But the question is, does this extend to other benchmarks and domains, right? Can we continue to build these kind of specific domains, small models? So if we go back for a second and compare OMAD to OMol, right? Both of these data sets have about 100 million samples or 100 million DFT calculations, but are they really the same, right? So in terms of, if you look at more granularly, OMAD has about a couple million starting structures compared to OMol, which is 83 million, right? So that's almost 100 times more. And then the number of atoms is also significantly larger, and with more complexity in this data set. So OMol is significantly bigger data set in terms of complexity compared to OMAD, which is like the leading data set for materials, right? So I'm going to assert that it's going to be very hard to use the same models to fit OMAD as you do for OMol. And we also observed this over and over again empirically. And also what this means is that if you look at in the current state of AI, right, in the last couple of years, the general trend is that larger data sets require larger models to fit. And these are called like scaling laws, with the most prominent example being from OpenAI, DeepMind, their work on scaling laws for LLMs. Right? And we've kind of done the same thing for MLIPs and showed that within a certain compute range, we can also get this scaling property where if you have larger data sets, then you need larger models to fit them. The other nice thing about having large data sets is that you get this inherent ability to generalize better, right? So we saw that we have all of these different data sets from different domains, and each data set have these different captures different types of pair of atomic interactions. Right, so for example, OMol, you have a lot of, so these charts represent like the different atomic numbers on the two axes. And so for example, OMol, you have a lot of interactions in kind of the organic element space. And in materials, you have this kind of, it's much more spread out. And if we combine these and add them all together, we get this UMA data set, which is like a very rich and diverse data set that captures a large range of interactions between atoms across all these different domains. So what's the problem if you try to build a model on this very large data set, right? And generally, there's two things. One is just naively training a model that tries to fit all these data sets at the same time doesn't work as well. And in particular for MLIPs, it's much harder than in like LLMs or vision, mostly because these different models represent different DFT levels of theory. So their labels don't even agree with each other. Right, and we've tried this over and over again. If you just train models, a multitask model, it always performs worse than a single task model. The second problem is the large models are really slow and they're huge memory hogs. Again, this is a much harder problem for MLIPs because we want to run these long simulations. And then previously the biggest model that we had, Equiformers V2, was about 150 million parameters, and it was just way too slow and couldn't scale past like a couple hundred atoms. So we introduced this thing called the mixture of linear experts to solve this problem. This is also not new; it's borrowed from other parts of ML. And the idea here is that we want to increase the capacity of the model without sacrificing speed. Right. So we want a very large parameter size model, but we don't want to incur that cost at inference time. So what we can do is we can pick a subset of those parameters at inference time. And the way we do this is through a list learn property through this global embedding. right? So we want to represent this input system in such a way where we can help sub-select the parameters that we want. And one special thing that we want to pay attention to here is we wanted that embedding to kind of stay constant if you want to run a simulation, right? And so we want to give it some information like what is the atomic composition, or what's the DFT level of theory, or the global charge and spin. And that allows us to kind of sub-select the parameter space. And so then we built this, with that, we built this universal model for atoms, UMA. And it was a very large model by MLIP standards, so 1.4 billion parameters for the medium-sized model. But the trick is at inference time, we're really paying the cost of effectively 50 million parameters. And that's going to give us the speed that we want and not sacrificing accuracy. So just a quick comparison. From the previous chart, we saw that naively training multitask models was really hard to get the accuracy up. And then if we apply this mixture of experts, we can actually now beat both the single task and multitask baselines. And this also gives us nice benefit for inference speed and memory, and we're really memory efficient and compared to like many of the single domain models, and the speed is also very comparable. Just a quick run through on some of the benchmarks. So the catalysis is like a big area that the fair chemistry team has been chasing for a couple years. And so we're pretty excited to get to this like target of accuracy of roughly 100 MeV of error. And so we were able to do that for this model. And then in material space, I think the MapBench discovery leaderboard is a little bit saturated, so it's harder to kind of push up these numbers, but it's still able to kind of get to the top here. And then, of course, this is pretty new for molecules. We just introduced these benchmarks. The model is able to do well in certain spaces, but actually not that well in others. And this is actually, I think, gives us a lot of exciting new areas for people like yourself to kind of make headways here. And again, so we're pretty happy with the way this model turned out, but I think there's still significant areas of improvement and limitations that we hope we'll start working on, and everyone in the field starts working on in the next couple months, years. And so one is like this idea of long-range interactions is really hard because we use these message passing neural networks, and there's an inherent limitation that there's always a cutoff radius by if you go beyond it, then the interactions no longer count in this model. Secondly, charge and spin handling was very, very naive. When we introduced this, we just added this charge and spin global embedding, and it overfits quite easily. So you'll notice that it kind of works well in certain examples, but then if you go out of distribution, it becomes, it doesn't work at all, right? So there's a lot of room for improvement there. And same as any other ML model, we're really good in distribution, but not so great out of distribution. Uncertainty quantification is going to be huge here. And then these models are fast, but still not that fast. So we would like to continue to make improvements on this area. All right, and with that, I'm going to hand it over back to Sam to talk about new areas.
Thanks so much, Ray. So yes, there are major limitations and a lot of work to be done here. But even still, let's look at what people are already doing with the models and they couldn't do before. So the first is the ability to capture charge and spin. In transition metal complexes, if you have different oxidation states, you expect, in reality, you're going to have different geometries. And for our models now trained on OMol are the first that can actually accurately reproduce the fact that a copper 1 should be tetrahedral here and a copper 2 should be square planar if you optimize the geometry. Also in the domain of charge and spin, in your batteries in your phone, you have ethylene carbonate. And when ethylene carbonate picks up an electron and reduces, the ring bond breaks. This starts the reaction cascade responsible for SEI formation, which is why lithium-ion batteries were able to be commercialized. No previous model could distinguish between the stability of a neutral EC and the reactivity of a radical anion EC. Those are just some examples that we put together right at release, but we've been really excited to see what people are already doing with the models. So 25 days after our paper and models and data sets were released, we saw a paper posted by a group in Japan where they used UMA to do transition state optimization of these complex terpenes, and they were shocked at how accurate the models were compared to their reference DFT. Very, very small differences in geometries and in barrier heights. That same group, about a month later, put out another paper showing even more examples of complex transition states, now also involving metals, that again were exceptionally close to their reference DFT, and basically saying that they didn't seem to think they ever needed to run DFT again, that all of these systems they were using it on, it just worked perfectly. So that's super exciting, certainly for me, someone who cares about complex reactivity. A little bit after that, we saw people doing these ML works using enzymatic transition states, again, getting shockingly good agreement with DFT, and in this case, I think also experiment. This group already has command line tools that you can just use right out of the box to look at some of these complex enzymatic reactions. And then this was just last week, the team at Orbital Materials now has a model trained on OMol, and they demonstrated that, in this enzyme, they observe CO2 binding to the experimentally observed zinc site, which no previous MLIP could capture accurately. So really cool to see other people training models on the data set and showing the power of those models that can do things that no previous models could. Also, the folks at Rowan have shown some really nice things about qualitatively capturing relative barrier heights of different reaction mechanisms in a transition metal complex. Also, one of the OMol contributors, Michael Taylor, has looked at kind of spin surfaces of these out of distribution transition metal complexes. And despite the fact that the current data set has no intermediate spin data, the models do okay for intermediate spin surfaces, which is pretty surprising and exciting. And with that, I'll turn it over to Aditi.
Thanks. Great. So the last thing that we're going to talk about is, where does the field go from here? So is chemistry as materials solved? I think we would all agree that there's still many, many problems left. And we're just going to highlight a few of the future directions that I think make sense to think about going forward, now that we have this very large data set and we're looking at what's next, what can we do with this beyond the data set. So one thing I want to mention is that there's been this really big shift in the field that I think is coming. It's mirroring many other fields of ML, what we see with language modeling, what we see with vision, where we had previously for many years in this field, you had these small, very constrained models that were trained from scratch on small data sets. And we've seen this big shift now, because we have the data, that we have a new paradigm for those same problems, where instead of always starting with training from scratch on small data, we can start with some large-scale model trained on many, many different types of data sets. We could directly use it right away, as with some of the examples that we just saw. We could try to get more accuracy with these models, because maybe there's small data and we fine-tune that large model on the small data set. So nothing is from scratch anymore. And one direction I think that is going to pick up a lot going forward is this idea of getting greater speed. So the models, like Ray said, they're doing well. There's been a decent speed up, but there's still a lot more to go for a lot of phenomena that we want to see. And one promising area for that could be the idea of doing some type of model distillation. And I think fine-tuning, to this audience, I'm sure people are relatively familiar with it. I'll briefly talk about how we could try to push that speed frontier further, because I think that's where there's a lot of gains to be made. So the idea of model distillation, I think this is in the future directions, is that we have these new models that are large, but they're still going to be too slow for really, really long timescale phenomena, especially when we think about how fast classical force fields are. And so the general idea here is that, could we take this large scale model? Now we finally have models that are large scale, and we can take those models and distill them into smaller specialized models that use the initial representation learned from the large model, but they're going to be much faster than the large model to use for a downstream task. And one of the key points here is that having this small model trained via distillation from a large model, it pretty much always beats the same small model trained from scratch on limited data. So this is this paradigm shift of no more small models, small data. We go to this new starting point and work from there. So one example of what this would look like customized to ML IPs, and I think there's still a lot of work to do here, is that if you do have this really large-scale model, like a so-called foundation model that's very slow, especially in this field, domain scientists don't really care about having a model that works on all of the systems in the world. You usually just care about one or two specific systems. And similar, maybe if you're researching a topic that you're plugging into your favorite large language model, you're researching very specific things, not everything that it was trained on. And so this idea of distillation could be that you have some procedure that takes your large model, distills it into a much faster and specialized ML force field. Maybe now instead it's looking at amino acids specifically or perovskites specifically. And that's the model that you use for all of your downstream applications. And this paradigm, I think, opens up a lot of possibilities that you get the accuracy of seeing all the data, but you get the speed at the end of getting something very fast for your specialized task. And I think one reason this direction is quite exciting is because you can see in the past, so the large scale model was not very large and it definitely was not as good. And that's represented in the pink over there. And you could take a model and train it from scratch, represented in the orange dots over there. So we would like to get lower error, so lower is better. So that model trained from scratch is not as good as the large scale model. But the large scale model, even though it's more accurate, it's still quite slow because we'd like to get to the right-hand side as much as possible in terms of speed. And if you do this distillation procedure, you're essentially getting the accuracy, or sometimes more accurate than the large-scale model, but you're now much, much faster. And so I think this paradigm opens up lots of nice possibilities because the large-scale models, as we just saw with UMA, are much, much better than they used to be. And there's plenty of examples where you could take this paradigm of your large-scale model, do some distillation procedure to speed up everything, and many applications where we've already seen some very interesting results so far doing this with electrolyte systems. So these are, for example, the things that appear in batteries. It will be in your phones or computers. To study these systems, you often require very, very long timescale simulations to run with molecular dynamics. And this is a very good use case of trying to take a calculation that with DFT it would be completely intractable. It would be years. With a large-scale model like UMA, maybe it could be a month or a few weeks. And with this plus this distillation speed up, maybe you can get down to days in the end. And so we're seeing this. This is a really exciting time to be chipping away at the speeds that we can push these models. Other similar examples are like protein-ligand interactions. So this is where if you do anything with proteins, these DFT is way too slow. Even running these ML IPs is very slow compared to classical force fields. But maybe we can push that limit of speed and get closer to studying these systems at the proper time and length scales. And this was all about inference speed. So how can we really push the speed now? And I think this is a big thing going forward, really pushing the limits of the speed of these models. But the other axes that we want to look at is length scales. So if we can make these models learn from really, really large systems with a huge number of atoms, that would also give us much more representative behavior of what we think would happen in the real world. So I think these two axes are going to be the next frontier of what we try to do with these ML IPs. Push speed as much as possible, but also can we scale it so that we're looking at as many atoms as possible as well. And if we could do both of these at a very fast speed, I think that is now where we're really talking about revolutionary work in the space of chemistry and biomolecules, materials, and so on. So one thing that we haven't talked about that much, because the focus of this has been on ML potentials, but I think there's also a lot of really exciting work that can be done in the generative modeling space. So the idea of generative modeling is that you can just directly generate the samples that you're looking at. So one example of this would be that you generate an image that corresponds to some text prompt that you cared a lot about, or you typed in a text prompt, you immediately got an image. And while each step of molecular dynamics can be faster with these ML potentials, potentially adding things like distillation, there are certain types of states that might require many, many time steps, maybe billions of time steps to capture those high energy structures which are still physically relevant. And so I think this data set also opens up some exciting possibilities for generative modeling, where we can sample directly from these systems which are represented by a Boltzmann distribution and directly get the structures out that we care about. And we now have this open molecules data set, which is a good grounds for training generative models as well. And there's been some nice work in the MD space on showing how you can use these generative models. You could sample the configurations directly. You could sample transition paths, so things representing behavior like chemical reactions or protein folding. And you could also try to doing this type of inverse design, where you try to design new systems based on properties that you care about. I think this is a wide open space, and I think it'll also definitely grow more now in the next coming months and years. One other point, a big direction going forward that I think this is really where community input is super important, is the need for better benchmarks and evaluations, especially against experimental data. So a lot of the evaluations of these MLIPs often looked at what the error was on the energies or the forces, and this was a first level proxy. Now with open molecules, we have a set of additional evaluations that are going beyond that to give you more faith in the benchmark, and more people are coming up with better evaluations. I think one thing we need to really think about is how do we benchmark these against experiment? And I think that'll be one of the next frontiers as well. Can we actually trust these models? They're doing things that actually match up in the lab, in experiment. And now we have a really robust cycle of being able to actually use these models to do cool new science. So I think building benchmark data sets and having them be rigorous, having these evals be rigorous, it's made a huge difference in many other fields of machine learning. And I think we're seeing similar progress here. And this is something where I think community input would be hugely impactful with connecting this to the real world. And the last thing I'll end on is I think there's still lots of open problems on what are the best approaches to learn from all of this data. So open molecules has so much information already represented in the data. And do we actually know what's the best way to learn from all of it? So far, mostly the energies and the forces have been the things utilized in current models, but there's many, many other things there, like the charge, the spin, multipoles. There's huge charge densities that are going to be released, as well as the wave functions and Fock matrices. And so all of this is very, very rich information that could go in towards building models that are much better than anything we had to see before. And I think there's many open questions left on what's the best way to learn all of this information from the data, especially at this type of scale. What are the design choices? What are the mechanisms that we need to use and create to build methods that can actually utilize the tremendous amount of information in this data set? So I think this will also be a really fun area going forward, and one that I think is very fruitful into maximizing the ability of these models. Great, so on that note, we'll go ahead and end there, and I think we'll be doing a panel discussion after this. Thanks.
Just take a seat.
Hello.
All right. Well, that was fun. So the plan now is we have this one question that we'll kind of chat about, and then we'll open it up to questions from all of you, and we'll stick around until you're sick of hearing us talk.
Also, if you want to chime in on this, so we can be a little bit more like back and forth rather than just us talking, right?
Yeah. Feel free if when we are saying stuff, if you think that's a bunch of baloney, feel free to raise your hand and we can chat about it. But we just kind of wanted to start off with the question of kind of where do we see the field headed, and how should industry, academia, and government work collectively to best accelerate science? I'm going to let one of the two of you kick us off.
So I can say what I'm really excited about, and I think Aditi already pointed this out, is this ability to kind of scale simulations from AIMD to like classical scales, where we can simulate like viruses, proteins, like all sorts of things at the kind of mesoscopic scale, and for time scales that really matter to these these types of molecules. And I think it's going to take a lot of work in terms of both like making the models more accurate and making them faster. And I don't think I think there's some speculation that, hey, maybe with these models in this data set, the DFT is the DFT surrogate is done, right? We don't need to work on this anymore. And I think that's absolutely not true. From what we've seen, the models are, they're just like other ML models in this space, where they work really well in the model, in the data they train on, and not so well when you go out of distribution. And so I think there's a ton of work to be done there.
Yeah, I think one thing we might see shifting, very similar to every other field of machine learning now, is what are the best problems to work on. I think for a long time, there was a lot of model building going on in this field. Everyone would build their new favorite model with something slightly tweaked from many other models. I think that starts to not be as useful now, because we have a very, very large data set, and we have much better evaluations and benchmarks on this data set. So I think one thing going forward is also just to think about what can you do beyond model building. There's many, many applications. There's many new methods that you can build on the current models. And I think this is also worth thinking about if you're, for example, an academic or at the national labs. This is probably a direction that is more meaningful for you with the compute budget that you have, versus now we're seeing very large-scale engineering efforts to train on these huge amounts of data.
Yeah, I think that people sometimes feel in academia or at the labs that it's like hard to compete with the folks at the companies, but I think it's important to be strategic. Like, you shouldn't be competing. The team at Meta is not going to go and do the science and like solve the problem. They might do some science, but there's a lot that can be done. I mean, even if we're just limited to in distribution, OMol is so big and so diverse that in distribution is shockingly wide. I mean, even in the context of, for instance, metal organic frameworks, there's other data sets that are specifically MOF data sets for MLIPs. But we've played around with OMol, and actually it does really well for MOFs, maybe because transition metal complex local environments don't look that different from MOF local environments. So, I think if you can, there's so much space to do science, and the people who kind of pick up these tools and push them and see what can be accomplished are going to be really rewarded with for that. I do think on the model building side, scale needs to be prioritized. Like, I think that we've had kind of computational chemists and computational material scientists who are guided by chemical intuition around perhaps the importance of equivariance or kind of physics infused architectures. And now that we have so much data, we may need to be prioritizing just the ability to learn as well as possible from the data, and maybe removing inductive biases. And perhaps that's where more computer science focused people may be better suited, rather than us old fashioned chemists with our chemical intuition.
Yeah, I think that'll definitely be a shift in the field. This is, if some of you may be familiar with the bitter lesson, which is this idea that putting these domain constraints may not necessarily win in the long run, versus coming up with ways to scale models and learn effectively from data. And I think we're starting to see some of that shift in this field now, and it's something to keep in mind going forward with projects you work on. One big advantage that I think people not in industry have is you have the exploration capability much more. You can explore much more on projects. You can try random directions, and if they turn into something, this is great. And I think this is something that is definitely worth thinking about going forward in terms of being creative with the research directions that you work on.
I'll make a bit of a counterpoint on that. And I think scale is important, but I think like physical grounding is it's equally important, right? I don't think, it's maybe just my opinion, but I don't think LLMs are going to be able to learn physics and chemistry anytime soon. And we've seen this over and over again. Like, for example, why is equivariance important? It's not that you can't learn it, it's just you need a lot more data, and it's a lot more data efficient to add it, right? And the other example is like learning, trying to train a model on energies versus, let's say, training a model on like Hamiltonians. right? When you have a lot more label and a lot more grounding, the model generalizes a lot better. And so I think having that, like finding ways to add the physical grounding in the models, even if we scale them, I think is still very important.
Yeah, I definitely agree with that. I think I'm like have like the angel and the devil on my shoulder of like, oh, chemistry, like real physics and chemistry kind of still matters. And that's why we saved all this information, right? I mean, at the beginning of OMol, we were talking about it and people on the meta team said, all right, Sam, like what should we save? I said, everything? Could we just save everything? And they're like, yeah, sure, I guess so. And then, halfway through data generation, suddenly there was a panicked email saying, oh my God, the AWS bill. Like it's too big. But we did save the wave functions and the densities, and I think that's going to be a huge opportunity for the community. On the other hand, I'm not sure anyone is going to be able to train on 100 million wave functions anytime soon, but I would love to see it. But that's probably where maybe, if you could demonstrate it on a smaller scale in the kind of this academic environment where you can take these kind of bold and high-risk research directions. And then if you have some strong preliminary results and maybe you come to a company, that could be a really strong grounds for a collaboration, where you've kind of done the work to proof of concept, demonstrate the idea, and now it's like, hey, can I get some of those resources, and can we really push this forward?
And I guess following up on that and also Ray's point, I think just a general phenomenon is that methods that work at small data scales often don't work at large data scales. And what we see often is that not putting as many domain constraints into the models at large data scales ends up meaning the models learn better and learn more from the data. I think this is still an open question to figure out what that balance is in this field going forward. But I think it's worth thinking about it now, because I think it's easy to get caught into like a very principled framework of I can write down all the physics, therefore it has to be in the model. But I think at the end of the day, we can evaluate the models based on benchmarks and evaluations, and that should be our metric for really seeing how well the models do. And that may or may not be with embedding constraints versus learning it very well from the data.
All right, maybe that's a good point to open it up to questions from the audience.
Hey, is that working? Yes. Oh, great. Thanks so much for this. I was excited about pretty much every slide. It's just incredible how fast this field's moving. Two questions. First is pretty specific. I know for a long time everyone's been training on energies and gradients, and then recently there was kind of discussion about whether to train on Hessians as well. I'm wondering where the community came down on that and what your opinions are on that specific question. And the second question is more general, what you guys think about ByteDance's new force field that recently came out.
Ooh, I have thoughts on both of these. We've trained models on energies and forces, and they do quite well on Hessians. So that's something that's not currently in the OMol paper, but we're going to have a non-stationary point Hessian eval specifically on the OMol leaderboard. Still working on it, but my gut, which is about 50-50 if it's worth anything in the machine learning space. In chemistry, it's like 90% worth something, but at ML, 50-50. My gut is that we don't need to train on Hessians. Also, just the DFT cost of the Hessians is brutal. People have put out there's at least one Hessian data set, but it's at a crap level of theory. Now we've got 100 million high quality energies and forces. I think we're going to be fine without training on Hessians. Also, the training cost once you're doing Hessians becomes crazy because now you need third derivatives during backprop. And then the ByteDance's force field, I love the work coming out of the group of ByteDance. I love their Bamboo MLIP, and I'm really excited about their force field. I think they're very tailored to kind of the contracts they have because that's like the suppliers and that they want to serve. But I was really interested. They still, even with a force field, trained with the latest ML techniques and decently high quality data, they still couldn't predict some of the transport properties, experimentally, and they kind of had to further align their model on experimental data. I thought that was pretty interesting. So I think they're doing amazing work in the electrolyte space, and I think it'll be really cool to see other groups try and also contribute there. And if we really do need to basically be training on experimental data to be able to predict these things, or if better architectures will get us there.
Did they train that polarizable model on OMol25?
No.
Okay.
Yeah, I mean, I pretty much agree with this. I don't think we need to train on Hessians unless there is a strong benefit. And yeah, the cost, the computational cost is just extraordinary. And then in ML, whenever someone introduces Hessians, the next, like in 1 year, the next year, they like people stop using it immediately. So like, yeah, that's just the kind of the trend. Yeah.
Yeah, I think I agree with both the points. I think getting the Hessians in the first place is expensive. Training on it is another step. I will say one thing that we've found is when you do some type of model distillation, doing it with Hessians does much better than doing this type of distillation with just the energies or just the forces, so the gradients of the energies. Some of that might be partly because you're now specializing to a smaller data set, and so the Hessians become more important as the biggest knowledge transfer from the large model to the small one. But you also have to do a lot of subsampling and sketching techniques from numerical linear algebra to make this pretty fast.
I'll echo that. It was really exciting and great work. Thank you. I have two separate questions. One is kind of an uncertainty quantification, and I fully appreciate that kind of completely out of distribution uncertainty quantification is kind of an open problem, probably too hard, but at least I'd love to hear your thoughts on kind of current advances or ideas, at least on how to get a little bit of uncertainty estimation from these models when they're being used in inference, so that we're not only basically doing post hoc validation via more expensive methods or experimental results, but having some sense of kind of the quality of calibration and uncertainty of the predictions once we're starting to drift outside of the actual data, but perhaps not too far crazily out of distribution. That's kind of question one. And the second one is on the topic of long-range interactions. I'd love to hear if you've seen any work or what directions there are regarding kind of some of the traditional advances that were done in, say, fast multiple methods and multi-resolution techniques that really kind of in classical numerical analysis and physics codes did a pretty good job of helping us get a grip in that balance between long-range interactions and speed, and whether any of those ideas are kind of like making inroads in this space. Thank you.
Yeah, I mean, the UQ is a really hard problem. Unfortunately, I don't have a good answer. I mean, like, I think from the work that we've tried and work that we've seen, so far has been there's the simple methods of, doing many predictions, right? And then getting the statistics from those. And I think they've worked in like limited circumstances, but I honestly don't have like a good solution there. I mean, if someone does, I think this is like going to be a huge breakthrough for the field. Yeah. I don't know if you guys have any better idea.
I got nothing else on UQ. Do you want anything else to say on UQ? Because otherwise we can talk about long range.
Sure. Yeah, I think I would generally agree with that on UQ, especially at large scales. Like some of the ways people would do UQ in the past was maybe doing an ensembling method with a bunch of networks. You figure out where they disagree. This becomes very intractable at large scales. So I think coming up with a better method would matter a lot, especially now that we're at this 100 million scale of data.
For long-range interactions, I mean, I think that this is a really exciting area. Certainly people like Bingqing Chang here at UC Berkeley have done some great work where, you don't have to train on partial charges or spins, or I don't think she's done any work in the spin space yet, but you just kind of learn these latent partials and put in Coulomb and see how well, and it provides benefits. But we haven't seen methods like that really trained at scale yet. So, I mean, that's something that Aditi and I are collaborating with Bingqing on right now to see if that's, because it is, if you're building Coulomb into your energy function, that is introducing an inductive bias, right? So it kind of begs the same questions around what's the right way to learn it. We are seeing, so right now, the models, if you simulate liquid and electrolyte densities, they're too dense by about 8 to 10%. But like the R squared is almost perfect. So it's just systematically everything is too dense. Now, at first we thought maybe that was because of the VV10, non-local dispersion, which can overbind many body dispersion. That's the density functional, used to generate the OMol data. Omega B97MV remains kind of the king of the DFT functionals, of course, created by Berkeley's own Martin-Head-Gordon, but VV10 is known to overbind many body dispersion. But there's, the other hypothesis is that because the models have no way to learn long-range interactions, that they are kind of they're kind of compensating by learning an overly strong short-range interaction. And, for instance, there's this PLA15 protein ligand binding benchmark, and the GEMNet OC model, which has a 12 angstrom cutoff, does way better on that than the UMA models, which have a 6 angstrom cutoff. And so that the UMA models overbind, just like they are overly dense. But the GEMNet OC model is much closer. It is not really overbinding. So that makes me hopeful that this isn't a data issue, but it's an architecture issue. The way to solve it, I don't know. I mean, all to all attention. I mean, there's a lot of, exciting directions that people are looking at. We'll see. That's what we hope the leaderboard will show, our people are going to compete on it. So.
Yeah, I agree with that. And I think, this is like some work that Aditi's group has also been working on, right? Is going away from this kind of fixed cutoff and just letting the model be able to use much neighbors that are much farther away, and doing that in a very natural way and not have these, we learned previously that having any kind of discretization really ruins the potential energy landscape, right? So doing that smoothly is going to be really key.
Yeah, definitely. I can tease a little bit of a result. I don't know if this is recorded or not, but we have been working also with people at Meta to come up with ways where you can actually learn this from the data. And one of the ways you could do that is actually by greatly increasing what each atom can see. So if each atom can see the whole molecule, you could actually tackle long-range interactions. Now, how do you do that efficiently? This is, I think there are some exciting results that are going to come out soon showing that doing it this way lets you learn a lot from the data in and of itself without having to necessarily build in certain things into the model.
Yeah, thank you for the wonderful discussion. It's been really interesting. I had a question about LLMs in chemistry and material science. So I think you mentioned that they don't do really well. So how would you define good or bad? And I think our experience has been that they're actually pretty decent in some tasks in chemistry. So yeah, that's just a question to the panel.
Do you have a specific thing that you're thinking about where it's doing really well, or is it not doing well?
For us, it's in reticular chemistry, and they're quite useful in certain aspects, extracting data, structuring data, also as evaluation agents. So how would you say they're bad then? But it's sort of use case dependent, I guess.
Yeah, I think, as you said, LLMs are good one is they're good in the context when there's a lot of text information that you can extract and it can learn from, right? And then the other parts where it's good, it's when it doesn't need to be extremely factual, and then if you can depend on if you can use it in a combination with these potentials. For example, I think a lot of people have been doing work on where they use an LLM agent to call ML potentials and then to kind of learn interactions between atoms. I think in those cases is going to be really powerful, right? But I think the ability for LLM just to learn from text on the interatomic potentials of atoms, I think that's going to be a really hard problem.
What's larger, 9.11 or 9.3? Let me know when they can answer that correctly, because they still say that that 11 is larger than 3. So not great. I agree with Ray. It's I'm not an expert at all, but when there is one correct answer, one correct numerical answer, seems like they don't do super well versus when it's a matter of opinion or expounding on something. But I would love to see these things come together. I mean, one thing I'm super excited about and interested in is how can you bring kind of the power of LLMs and images and text, and obviously those are super useful. We all know that, right? And MLIPs and DFT data and experimental data. And it feels right now that we have all this disparate data and kind of models trained on disparate, there's kind of islands of data where you can train a model on this island or a model on that island, a model on this island, but it should all be useful. And then I see proposals of people saying, oh yeah, we're just going to throw it all together and mix it in a pot and train a model. And That's not going to work. Like, we're going to have to be smarter than that, right? So what does that look like? I don't know. Really interesting question.
I wanted going back to, I don't know, you called them surrogate models or something like that, and you hinted that maybe on MOFs actually extracting a model from this big database did pretty well. Could you be more precise? So because there is also coming out of Meta a few years ago, this model for MOFs. So is the current model, if you then distill it onto MOFs, better than the previous model? So that would be an interesting question specific. And then sort of a more open-ended questions. When I wanted to deal with experiments, could I think of that in a similar way, that I have sort of these models you have trained on many DFT data, and now I sort of want to teach a student model which actually applies to the set of experiments I'm interested in.
Let me weigh in on MOFs real quick. I am by no means a MOF expert. I think we have a couple in the audience. But what we did, we played around with, so there's the ODAC23 data set, and now then just like a month ago, less than a month ago, now the Meta team released the ODAC25 data set, which kind of cleans up some of the convergence issues and expands some of the adsorbates and some other stuff. But it's PBE plus D3. Right, and OMol is omega B97 MV, so it's just it's a higher level of theory. It's a more accurate with respect to, for instance, coupled cluster underlying level of DFT with kind of a more sophisticated description of dispersion, and these are the types of interactions that are going to drive gases binding within MOFs. Of course, there are no MOFs in OMol because MOFs are periodic structures, and everything in OMol is a localized molecular structure. But an MLIP doesn't really know the difference between a periodic system and an aperiodic system. Each atom just kind of sees its local environment, and as long as your PBCs are handled correctly, then that's still just a bunch of local environments, right? So we ran some simulations of like Henry's law coefficients using the UMA OMol and UMA ODAC, and this was still ODAC 23, and against experiment, and we got better agreement with the OMol with UMA OMol than UMA ODAC. Now I'm trying to start up a collaboration with some folks at Meta and with Kai-Heng Shi at Buffalo and others, basically doing full isotherms. And there we can really start to evaluate the predictive capacity of these models, against experimental isotherms. Because the issue also on the MOF side is that the DFT benchmarks are all PBE plus D3. So you can't compare an OMol trained model to those because the thing you're comparing against is a lower level of theory. So of course the model trained on data from that level of theory is gonna match it. So it comes back to the importance of actual experimental benchmarks and seeing how well these models predict reality.
Yeah, also unqualified to speak for MOFs, but I think this point that Sam made about we have these data sets that are trained on periodic structures, and then the ones that are trained on aperiodic ones that uses different DFT level of theory. We're really hoping that, for example, if we combine the materials data set with molecules, that then we can handle something in between, like molecular crystals, right? And MOFs also kind of fall somewhere in there. And I think it's not that obvious that it works that way, but this is, I think, something that we really want to get right. Yeah.
You also asked about something besides MOFs, but I was totally focused on the MOF answer. What was the other thing that you asked, Christian?
No, my question was whether we could think of explaining experiments in a similar sort of conceptual way, that we say we have these big models trained on all these data sets. Now I want to come up with sort of a small model where my data are small data from a particular experiment, but maybe by using your big model, I actually can solve a problem which otherwise would have been very hard to solve.
Yeah, I think that would definitely be a good use case of it. Actually, MOFs, I think, are a really good use case of doing any type of model distillation, because to compute the transport properties, you do need very long timescales or very big systems. So I could see those two things being very nicely coupled together. I think this is I wouldn't say right now whether it would work or not from this moment, but I think doing it this way with the large model, doing some distillation, getting those properties, I would be 99% sure that would work better than just trying to do something with the small model?
I'll just say briefly, I mean, I think I'm super interested in taking a large pre-trained model trained on DFT and trying to apply it to experiment. I mean, you know, we've got a collaborator in the audience right now. We've been trying to take UMA and kind of fine tune it on experimental enantioselectivities. selectivities. So you basically just use kind of you can use the MLIP itself to generate a optimized 3D structure of some homogeneous catalyst, you know, the reactant in your reaction, which can kind of go to 2 different products. And then now we have experimental data with labels of, you know, the delta G's basically. You can just use your representation from your pre-trained model and then fine tune a new prediction head to be able to predict that delta G. It's not trivial. We're working on it, but like in principle, it should work better than training from scratch because you just have this super, you know, information-rich representation, and you can just repurpose that representation to do a prediction of a different property. So, like, I think that's part of what, you know, some of the slides that Aditi had. It's a paradigm shift, right? Don't like again, engineering still to be done, right? And science as well, but like don't train small models from scratch. Everything in principle should start from a big model and leverage that amazing power, and that should just improve prediction capacity across the board.
Okay, with that, I switch from an interested audience to the organizer. So I want to thank all 3 of you. And with that, well, please come back for our other seminars. Next week, we'll have an interesting seminar on the physics sides, how you can sort of use crazy AI to create experiments which you think might never work and then actually detect gravitational waves. So if you're a physicist, that sounds really interesting. Come, it will not be here because eventually we want to get you guys used to come back to our room in 373. So please come back for the rest of semester. And now I want an applause for our 3 panelists, and you are welcome to continue discussing outside.